Hello friends, this is Bhuvanesh Oza once again coming back to you with tutorial number 5, short tutorial number 5 on relay setting calculations of settings of ground overcurrent relays. In last tutorial we talked about the considerations to be made, or rather what are the considerations for deciding the relay settings for ground overcurrent relays that we talked about. So that was the theoretical part. Now we would want to go to one numerical to know how do we calculate the relay setting for a simple network once again. Because friends, we are slowly reaching to the difficult networks. Right? So we start with simple networks and probably end up with little more complicated network. No doubt, it is not possible to talk about or to rather take a tutorial on interconnected system like that in Gujarat state, or for that matter any other state, or in India. You see, because there are 50, 60, 70 transmission lines and some 100, 120 relays. And when they are to be coordinated, it is not a business which can be done I mean, it cannot be done manually. You have to resort to some computer algorithm. But then we will certainly talk as to why we have to resort to such computer algorithm. What are the problems those are seen in interconnected systems? That certainly we would like to see. But till then, right now today, only ground overcurrent relays, friends. So figure in the next slide will see the single line diagram of simple power system. We have got three relays R1, R2, R3, and they are standard IDMT normal inverse relays, right? And each relay group is wired in 3 overcurrent and 1 earth fault protection scheme. That is 3 relays for phase purposes, R, Y, and B, about which we have talked in earlier tutorial, and 1 relay dedicated for earth fault protection. Right? So finally, how the earth fault protection is done and how to decide the setting for the perfect protection in case of LG or double line to ground fault. The setting range of ground overcurrent relays we are assuming in this particular example 10 to 40% in 7 equal steps, that is 10, 15, 20, 25, 30, 35 and 40. No, obviously. Right. We are talking about the old electromagnetic or static relay. But if you have the numerical relay, you can have the steps like 10, 11, 12, 13, 14, 15, 16, like that. Many steps are, I mean, quite possible, right? And not only 10 to 40%, but you can go from 5 to 80% or 5 to 100%. I mean, quite a wider range is possible. That we talked about in last tutorial also. I would like to remind here once again. But here we assume this 10 to 40%. The excitation current of all CTs is 0.05 ampere. That's what we assume. You can assume 0.03 also, or you can assume even less, because 0.02, I mean, CTs with excitation current 0.02 ampere are available for protection. It's not so that they are not available. You can. So, but we have to assume something. We are starting with a realistic assumption of 0.05 ampere. The minimum operating time of IDMT relays, because DMT, definite minimum time feature, is there. So beyond PSM 20, the time of operation is constant, right? It is 2.3 seconds at TMS equal to 1. Because you see, definite time overcurrent relays have their own advantages. You see, pure inverse relays, if you go for IT equal to constant, then for I, which is 100 times the set current, the time of operation would be so low that it would be impossible to set the relays, to grade the relays. Therefore, definite minimum time feature is a must. Now here it is 2.3 second electromagnetic and static schemes. In numerical relay, it is adjustable. You can go for 2 seconds, you can go for 1 second. It is adjustable. So adjustable minimum time is there in numerical relay. But we have to start with certain assumptions, my friends. So I go with 2.3 second minimum time. That means if the PSM is more than 20, time of operation will be 2.3 seconds only. It will not reduce. It will not follow inverse law. Right? At TMS equal to 1, no doubt. If TMS is 0.1, then time of operation is 2.3 and 2.1, that is 0.23. Very obvious. The TMS of relay R3, we are assuming that it is set at 0.2. The fault currents at different buses are also shown in the next slide, right? So if we see the next slide, these are the fault currents for A, B, C, D buses. Fault current for triple line fault, fault current for double line fault, and fault current for LG fault. Here, for our purposes, we will consider fault current for LG fault, because double line and triple line are to be used for phase relays, not for ground relays. So here we will consider the fault currents for LG fault. So these are the fault currents. So our system is this simple system is there. 120 megawatt 11 kV generator, right? Stepping up to 132 kV by 150 MVA GT, right? We come to bus A. From bus A, many lines are going, but here I am showing only one. So let us see that. Let us be. I mean, here there are no more lines shown. Therefore, in this particular example, we will assume that only one line is emanating, 132 kV line, on which there is a relay R1 using 750 bar 1 CT. Then that 132 kV line goes further at substation B. It's a switching substation. There is no transformer. Right? We are assuming that there is no transformer. In the next tutorial class, we will take a transformer and see what is the effect of transformer on settings of ground relays. That we will see in the next tutorial, so that we go ahead in steps, right? We would like to go ahead in steps, because those who are in industries, those who are already working in industries, and those who have their plants, probably this would be too simple for them. But those who are students, I have seen, because I have worked as a teacher for 26 long years, and I have found that students are finding very difficult to calculate simple PSM, plug setting multiplier. Do you get me? I say that my CT is 300 bar 1 and fault current is 3000 ampere, and my relay is set at 100%. What is the value of PSM for fault current 3000? That is a very simple thing which they are not being able to calculate, because plug setting 100% means 1 ampere in secondary, 300 ampere in primary. Fault current is 3000. 3000 upon 300, that is fault current upon plug setting, becomes the plug setting multiplier. But this simple calculation students are failing to do. So obviously, because our learning skills, we have not utilized our mind skills, our intellectual skills. The students are not utilizing, probably. That is the reason why. But if some good teacher is available to them, he will make the students to learn many things. So friends, we are taking simple system, 300 bar 1 CT, second line R2. From there, two other lines are going. One is going to 10 MVA substation, right? And another is going to 50 MVA substation, right? From bus C also, three lines are emanating. One of the lines is going to bus D, on which there is 100 bar 1 CT, and I have got relay R3. I am now talking about ground relays R1, R2, and R3. That is the fourth relay. I am not talking about phase relays, my dear friends. Right? So, if we go further from here, what is the solution? Plug setting of R3 you have to assume, because you see, plug setting of R3 does not depend on normal load current of that line CD. It has nothing to do with that. We have already talked about, because under normal conditions IR plus IY plus IB is 0, and therefore under normal condition current passing through ground relay is 0, because it is connected in residual circuit of 3 line CDs. Right? So you have to assume something. Therefore, we assume minimum 10% and we go on with the minimum plug setting R3 10%. That is available on relays, 10 to 40% we have assumed. Therefore, 10% of 1 ampere, right? Because my CT is 100 bar 1, secondary is 1. So 10% of 1 ampere is 0.1 ampere. So CT secondary required to inject this current 0.1 through relay. CT secondary current 100 bar 1 CT in secondary. What will it have to inject? It will have to inject 0.1 that is required for relay plus 3 times 0.05. I'm sorry, there is an error. 3 times 0.05, that is 0.15. That will give me 0.1 plus 0.15, 3 into 0.05, that is 0.15. So the CT secondary current at relaying point R3 is 0.25 ampere. I would request the listeners to make correction in this slide because that I I just missed that. The excitation current is given to be 0.05 and not 0.5. Right? So 3 into 0.05. But the calculation is correct. 0.1 plus 3 into 0.05, that is 0.15, is 0.25. That is, the CT secondary current at relaying point R3 is 0.25. If I take that 0.25 to primary of 100 bar 1 CT, it obviously becomes 25. Very natural. 1 is 100, so 0.25 is 25. Therefore, the plug setting of ground relay R3 finally, I am coming to the fact that plug setting of ground relay R3 in primary terms is 25. My dear friend, it is not 10, which we were taking in phase relays. When I say plug setting of R3 as 100%, I was taking plug setting in primary terms directly as 100, which I cannot do here. I cannot take 10% is 10. 10% of 100 becomes 10. But we have seen that here the plug setting in primary terms becomes 25. Therefore, plug setting of R2. Now, R2 and R3 are related because there is no transformer. Therefore, same formula. Plug setting of R2, my dear friend, plug setting of R2 is more than 1.3 divided by 1.05 of plug setting of R3 because that 1.05 to 1.3 is the pickup range which we have already talked about. Right, so 1.3 divided by 1.05 of 25 gives me 30.95 for relay R2 I am talking, right? For relay R2 I am talking. 30.95 in primary terms for R2. Take it to secondary of 300 bar 1 CT. That 300 bar 1, 30.95 becomes 0.103 ampere in CT secondary terms. Now 0.103 ampere is the current passing through secondary of R2. But through relay R2 it does not pass. Through relay R2 I have to deduct that excitation current requirement. 3 excitation currents. 0.05, 3 times 0.05. If you deduct from 0.103, 0.15, 0.103 minus 0.15, the figure is negative. It obviously means that the minimum setting of relay R2 is also 10%, which will be higher than 30.95. If you don't understand this setting, I would calculate in a different way. Plug setting of 10% for R2 I am taking is 0.1 and I have to add 0.15 to that, 3 times 0.05, so 0.25. 0.25 if you take in primary of 300 bar 1, that is 1 is 300, what is 0.25, that will become 75. 75 is obviously more than 30.95, so my condition is fulfilled, that is plug setting of R2 should be more than plug setting of R3, so that more than is fulfilled. So my plug setting of R2 becomes 10%. That is also 10% minimum. R3, I assume 10%. R2, I calculated 10%. On the similar lines, you can calculate. You can try it, my dear friends, because everything we will not do. You can try and you will see that it is also 10%. So all the 3 plug settings are 10%. So now we have to go to the time settings. What are the time settings? For time settings, what you have to do, you have to coordinate R2 with R3. Time of operation of R3 you have to find out. Add 0.25 to that, and based on that you have to find out the time TMS of R2. For R2 and R3, how will you find out time of operation of R3? For that you will have to find out PSM. PSM for which fault current? PSM for maximum fault current, and that is at bus C that we had talked about. Because the fault current at bus C and immediately after breaker does not differ much. They are the same, more or less same, because breaker is hardly 10 meters away from the bus, right? So at bus C, what is the value of the fault current? 1192 for LG fault. So I take 1192, my dear friends. I take 1192 fault current for coordinating R2 with R3. 1192, if I take to secondary side, 100 bar 1 city, it is 11.92 in city secondary. But through relay, 0.15 will be less. However, 11.92 minus 0.50 is just minimal, nothing. But theoretically, I must do. So I have done. And 11.77 is the current passing through relay. So what is the PSM? PSM is fault current. See, we have not gone in primary side. We had to come to secondary, must in ground relays. 11.77, that is the fault current. Upon 0.1, 10% is the plug setting. So my plug setting multiplier is 117.7, which is obviously much higher than 20. And I cannot take in my calculation formula 3 upon log 117. I cannot take because the time is constant at 20. So I take log 10, 20 only. Into 0.2 TMS I have assumed, or it is given in the data for R3. So 0.46 second is the time of operation of relay R3. If I add 0.25 to that, time of operation of R2 becomes 0.71 seconds, right? I have to again consider the same fault current because I'm comparing two relays for coordination. So for 1192 ampere in secondary of 300 bar 1, it becomes 3.973. 3.973 minus 0.15 becomes 3.82. And PSM of R2 3.82 upon 0.1, once again because R2 is also 10%. So PSM of R2 is 38.2. So my PSM of R2 is 38. So 3 upon log 38. But I cannot take log 38.2. I have to take only log 20. So 3 upon log 10, 20. PSM of log 10, 20 only I have to take. Into TMS of R2, which is unknown, is equal to 0.71 because time of operation of R2 is already known to me, my friends. Time of operation of R2 I have already calculated, right? That it is 0.71, 0.46 plus 0.25. So 0.71 I know. So 0.71. Final time I know. So I can calculate TMS, which comes out to be 0.308, my dear friends. And I have to consider in steps of 0.05. So I go for the next step, 0.35. Had it been numerical relay, you could have gone in for 0.31. I do agree. You could have gone in for, but not 308, you see, because numerical relay also does not give 3 digits. Try to understand, right? So anyway, you will have to round off. But how do we round off? That depends upon which kind of relay you are using. So here we are assuming the old relays. You can assume numerical relay, I don't mind. And someday we will do all calculation using numerical relay alone. On that day we will configure the relay also fully, right? So that you may come to know how the overcurrent numerical relay is to be configured and what all is the requirement in configuration of the relay, because relay has many facilities. And to use all facilities, you have to fully configure the relay so that using those facilities, you can make your power system available for more time and thereby earn more money. That is, if you are the owner of the electricity company, you will earn more money. So 0.35 I have selected for R2. Now I go for R1, R2 coordination. For R1, R2 coordination, fault current immediately after R2, that is 1653 at B. 1653 at B I have to take. So 1653 I am taking 1653 R1, R2 coordination 1653. CT secondary equivalent of 1653 5.51 minus 0.15 gives me 5.36 and my PSM is 53.6, but I cannot take 53.6 because maximum PSM I can take is 20. 0.35 I know. TMS of R2 I have calculated, right? for R2. So my time of operation of R2 becomes 0.807. Adding 0.25, time of operation of R1 is 1.057. For same fault current, that is 1653. If you convert 750 bar 1 city, that is 750 is 1, 1653 is what? That is 2.204. And therefore, the current through relay is 2.204 minus 0.15, so it is 2.054. So your PSM is 20.54. You cannot take 20.54. You can take maximum 20 only. So your TMS of R1 turns out to be 0.458. And in the steps of next 0.05, we are selecting 0.5. So my TMS of R1 happens to be 0.5. I have calculated all the plug setting and all the time setting of all the three relays, right? We can calculate the setting of high set instantaneous units also. I think in the numerical next, we are going to talk about the high set units, right? So that you may get an idea as to how the calculations are done for high set units. Same formula is same as we were using in phase relays, but the fault current you have to consider is for LG fault. That is the only difference, right? So we summarize here. R1 is 10%, R2 plug setting is 10%, R3 plug setting is 10%. TMS of R1 is 0.2. Sorry, it is reversed. It is reversed. Once again, there is an error. TMS of R3 is 0.2. R3 is 0.2. R2 is 0.35 and R1 is 0.5. That's what we have written, because for R1 it is 0.5. So here in tabular form, I should write either I should change the relays R3, R2 and R1. I mean, that is the first relay is R3, second relay is R2 and third relay is R1. So that error, once again, I mean, typo error has occurred in this, and that I can see only when I'm delivering a talk. So I mean, it's difficult. I have to re-deliver, or I have to I have to make correction in my presentation. But I hope it is not very difficult to understand. Only thing you have to do is the first relay is R3, second relay is obviously R2, and the third relay is R1. Then everything is correct. But that is a summary. Finally, whatever we have calculated is nothing wrong. Everything is correct. So that is how you can do the calculations of settings of the ground relays. Right? Ground relays. How to calculate the settings of ground relays. Simple example. Next will be little difficult, little complicated. We will add transformer, right? And probably we may add high set instantaneous unit also in the next tutorial. So friend, till then, if you want to do practice on these numericals, I have given enough number of practice examples in my module 3 on transmission line protection, which is already uploaded on AdaptMe app. AdaptMe app is available on Google Play Store. You can download free of cost, and then go in for the my module 3. Obviously, you will have to pay for that. But then if you do that, then you will be able to do, I mean, many practice example, many questions, as I was telling in last tutorial, you will be able to analyze yourself as to where do you stand, whether you have understood all these aspects of power system protection. Till then, please, friends, stay tuned with AdaptMe, right? Because we will be going on for many more tutorials to come. To first complete transmission line protection using overcurrent and earth fault relays, then transmission line protection using distance relays, then transmission line protection using line differential relays, then generator protection, then transformer protection and whatnot, you see. Because it takes totally about, I mean, it's a course of about 70 to 80 hours. And these tutorials are hardly of 30 minutes each. Therefore, you see, I may have to take such so to say some 150 tutorial classes to talk fully about protection. But anyway, till then, thank you, my friends. Good day.